on this computer, yeah. So now, once we have formulated the problem, how do we find those W, all those coefficients? We have a formulation, we know that it models probability distribution, although we started by modeling, like implicitly by modeling log odds as a linear classifier. We're actually estimating probability distributions for each of the posteriors, probability of class given data. So whereas naive Bayes, also a powerful classifier, which can be linear, can be made linear, goes generatively, models prior of the class or estimates from the data prior of the class, and then likelihood. In logistic regression, we directly model parametrically, we model the posterior or the decision boundary. So an alternative perspective on log odds. I kind of dumbed it down and ridiculed in the previous part of the lecture that all we wanted to do is to find a way to fit a line and model, like imagine if our arsenal, like there is only one weapon in our toolbox is how to fit a line. Then we figured out how to model probability distributions with this tool of fitting a line. And we were in a very specific setting. But what we are in the general settings, we know nothing about probabilities and we don't model, this is just your standard Bayesian theorem of modeling posterior probability of class 1 given X. Remember our AIDS test example or our PML test example, or the boxes with fruits, whatever. Probabilities and likelihoods here. Posteriors can have any form whatsoever, as long as they're proper distributions. Likelihoods can have any form. Posterior is conditioned on all of this, of course, but can turn out to be any form. So let's denote our log ratio or decision boundary. Remember, the ratio of our posteriors is our decision boundary. But if we denote our decision boundary, actual value at this X as A, then we see that posterior is logistic function. It's a logistic sigmoid of this parameter A. Notice the generality. It's like regardless of what is the prior probability, regardless of what's the likelihoods or probabilities of the classes. If you denote your posterior ratio, log posterior ratio with a parameter, your posterior, well, this is class specific and this is your solution general, is the sigmoid, logistic sigmoid. So that's kind of maybe that helps. I hope that helps to emphasize the importance of logistic regression and logistic function, because it's so general. It's not just, oh, yet another method, learn it and use it in your toolbox. Although do use it because it's so easy. So sigmoid has nice properties. Again, we have log odds. So our decision boundary is actually modeling log odds. Sigmoid is a, well, it's easy to differentiate in terms of sigmoids, and help me there. So is it an odd or even function? No, it's not even an odd, but we can easily express, we can easily shift, I don't know, I need to check this after if the minus sign is there. Probably I meant to say this, that negative value is a shift by 1, but we'll check after that. Don't trust me on this specific formula, it looks fishy.
A half?
Yeah.
If you subtract a half, then I think it's an odd function.
Like I wonder in this expression if we set, if there is a plus rather than minus here. Okay, anyways. Not too relevant, but nice properties. We can express derivative of sigmoid in terms of sigmoid. So that's convenient because we can pre-compute sigmoid only once for the forward pass and the backward pass of backprop. For free, almost for free, we get the derivative and the actual value. And let's try to estimate it. Back to our almighty, all-powerful maximum likelihood estimation. So we have our logistic regression posteriors now for each class. We know how they are expressed, right? Those are sigmoid functions. We are going with the IID assumption. That's why the product for all of the samples. For each of the sample, we want to compute, we want to maximize the probability for each of the element in this sample, or for each sample x sub I. We want to maximize the overall probability of this data set. We want to change the values of W. But there are two classes, class 1 and class 2. So let's separate those classes into independent products, as we did with Bernoulli distribution. And if we express our probability as just sigma, you can immediately see, oh, look, this is a Bernoulli distribution now with some unknown parameter L1, which is probability of heads in Bernoulli, or we're just saying, okay, this is the probability of class 1, the prior, to be consistent with how I use my notation later. It's the pi. Like in the other slides, I used the pi there. Very, very simple, very quick, but is it clear? Clear? Yeah, nothing magical there. Well, we can't deal with those pesky products, so we just apply the log. Now we have some of the logs, and after I've applied the log here, and because of the rearrangement, I got the negative sign in front. So what do we see here? We see a function, or well, two functions that have, and again, that have this form, both of them. What does it remind you? Uma, you should remember, that's back to your question last time. Okay, those who don't remember, cross entropy. So now, not only thanks to Sir David Cox, 1958, and Marty McFly for traveling there, not only we have our softmax function that we still continue to use, we also have our loss, the cross entropy loss that we continue to use. That's the loss that the logistic regression using. This is the actual probability, the class probability prior. And this is what we're estimating, the pi and the sigma. The sigma is our function that we want to estimate, and we want to get as close as possible to the truth. So we're minimizing cross entropy loss when we're optimizing logistic regression. And most likely when we're training the modern over-parameterized models, we as well estimating minimizing cross entropy loss when we're estimating whatever the solving our classifier problem with our deep learning model. That said, let's differentiate this and solve it the usual way. Solve it by taking the gradient and equating it to 0 and solving for W. Remember, this is our logistic sigmoid, which is parameterized by the W vector. Blah, blah, it is here. Well, homework is go from this inconvenient and ugly component form to beautiful linear algebra expression, where you can just go ahead and solve the problem in any of your NumPy, MATLAB, or whatever you prefer, or Julia, if you want. But the thing is, it's kind of ugly. We can do better than just solving this. And let's try better for now. So when we're solving the gradient descent problem, we're going with a rough approximation to the function. We're taking a step along the line that is tangent to the current point, and then finding the value at this line after we're taking the step. But our function has, according to Taylor expansion, gradient descent is all like based on Taylor expansion. That's all we're doing. We're approximating a function with a Taylor expansion of the first order term, and this is what we're not approximating. And here's a visual example. With gradient descent, we're taking this line, taking a step along this line, checking the value of the function. But if we can take a step along the orange, I think the orange is this when we include another term. Those colorful lines, each line has more terms of Taylor expansion of this.
There's the third one. The second one looks like it's 0.
You mean the constant term?
No, the quadratic term. I don't see a quadratic term. But orange looks cubic.
Yeah. That's... No, like because it is a sign, it changes the sign. I think orange is just your flipped parabola or something.
No, it can't be, because you can only have one inflection point on a parabola, or you can only have one critical point, rather, not inflection point. And that says 2. It's definitely at least cubic, and I'm sure it's the cubic term.
Well, I'm not sure if it is the cubic term, but okay, the yellow is definitely after. It has more inflection points than the orange. But the point is, if we were using the orange instead of the red, this term instead of the line, then in one step we could be closer to the actual, well, one of the minima, to a local minima, than going by the line. And another important observation is that if you're optimizing a convex function, or concave, depending on maximizing or minimizing, when you're going with the tangent, you need to make a few steps before you arrive at the optimum. But if you're going with the quadratic term, if you're including up to the second derivative term in the Taylor expansion, then you can go to solution, often can go to solution directly. And that process is called NEWTON-RAPHSON method. And an aside, as always, almost in 99.9%, the things are not called for their inventors. Newton has nothing to do with this. Newton didn't know calculus that well anyways, and he did not invent optimization. So thanks to Raphson and thanks to, well, like seriously, the Nyquist frequency was just named by Shannon in honor of Nyquist, but Nyquist has nothing to do with it, and things like that. I mean, lots of things like that. It's
this is a long tradition.
Yeah, it's a long tradition. If you're thinking of how to name something, never name it for a person who invented it. Instead of, okay, so we have we have a loss function that we want to maximize in this case. Well, minimize. We want the likelihood. The L is the likelihood. We want to maximize the likelihood. We are at the point W, and we want to take a step delta. So if we, instead of taking first two steps of Taylor expansion, which we usually do for gradient descent, we'll add another one, the quadratic term, and take a derivative of this with respect to delta, of this expression with respect to our step, and set it to 0. Look what happens. This doesn't have delta, so it's not making here. Here, 2 and 2 cancel. We get this easy. Then express delta as a negative ratio of first derivative and second derivative, and make your step your new value. So you were here at W, and make a step, but now your step is expressed according to first two components or three components if you count the constant term of Taylor expansion, and then it's first derivative over minus first derivative over second derivative. It's easier said than done, because in the multidimensional case, when your loss is a function of a vector, it's still a point function. It returns a single scalar value, and I constantly use loss. In our case, it's likelihood. We want to maximize it, but in both cases, we want to find an extremum that derivative equals to 0 here. So in case of a vector function that takes a vector and returns a number, we use something called Hessian. It's an interesting matrix. It's a matrix of second derivatives. So we have our gradient and multiply it by inverse of Hessian. Very interesting method, and I want you to see how it works in practice, because you already watched the lecture of how would we find the optimal solution for a linear regression, not logistic regression, but the linear regression. Remember, when we need to fit a line, how do by minimizing mean squared error, how do we go about it? So here's our mean squared error. We want to find the W. Okay, we want to find this W. Given these values, we want to find a W that minimizes mean squared error. And of course, let's scratch that ugly component-wise form, write everything in the matrix form, combine our data samples as rows of the X matrix. W is a column of our unknown parameters. Well, X is given to us and Y is given to us. I just wrote the same thing in the matrix form here. Just please follow. Then we'll take the gradient. We'll find the gradient. Very easy. Just same derivative rules as you would normally use. And then find the Hessian, the matrix of second derivatives. So if we use the Newton-Raphson method and plug in inverse of the Hessian and our gradient times our gradient as our step and multiply through, interesting magic happens. We can get to the solution of linear regression in one step. In single step, no iterations, using Newton-Raphson method, we get to the estimate that is the optimal solution. Before, and this is called pseudo-inverse. Before, in one of the lectures, I forgot which one, I already talked about the pseudo-inverse and how to solve this optimally in terms of least squares error, optimizing the least squares error. Linear regression. Now let's do the same, exactly the same for logistic regression. We'll start with our formulation. We found the derivative sigmoid function and our data. That's all we have. And then, well, this is not 1, this is L, the labels, the actual labels, the vector of labels, 0, 1s. And sigmoid returns sigmoid function. It's also a vector of the value sigmoid function with given W returning at each of the x's. So it's a vector of values in the 0, 1 interval minus vector of binary vector of zeros and ones, just so you kind of follow me. And now our derivative will be second derivative, the Hessian matrix will be as follows, and W is a diagonal matrix now. The diagonal again is sigmoid at those corresponding values i's. And remember, this is nothing but value of the sigmoid with respect to derivative of sigmoid with respect to the parameter. Another fun fact about sigmoid functions, since it is the derivative looks exactly the same regardless of whether you take it with respect to W or to X. So now we have our expression of iterations of how do you compute W new value for the logistic regression given the old value. Let's do some manipulations. We're hoping that we'll get to a solution in one step. We'll take this out, we'll get an expression, and then do some renaming because we can compute these separately. And we sort of gotten something that looks like pseudo inverse, which we had before for linear regression, but it doesn't, because it involves our parameters that we optimize, so we can't solve it in a single step. Okay, or that we cannot solve it in a single step, but still we are guaranteed that this mock-up of pseudo inverse will get us to solution faster. So this is a pretty fast method for solving logistic regression, Newton-Raphson updates. Okay, what did we talk about? I don't have take-home points in the slides yet. I will add them for before putting the slides online. But the point of this whole lecture was logistic regression. Logistic regression is highly influential methods on everything that you are using currently and going to be using for machine learning for quite a while. And it has interesting properties, and yet it is super powerful by itself without all this learnable kernel, even without the learnable kernel of deep learning that you attach to it. But with deep learning, of course, it is a more powerful method. So that's all I wanted to say for the record. Let me stop it, and then we can maybe share our fears.